In this lecture, we will discuss reactivity of alkenes, addition versus elimination, and thermodynamic perspectives. All alkenes have a common feature, a carbon-carbon double bond. The reactions of alkenes arise from the reactivity of the carbon-carbon double bond. The orbital picture of an alkene looks like this, showing the head-on overlap of hybrid orbitals to form the sigma bond and the sidewise overlap of the unhybridized p orbitals to form the pi bond. The electrons in the sigma bond framework are tightly held, while the pi bond is delocalized above and below the sigma bond. The pi bonding electrons are separate further from the carbon nuclei and they are more loosely held. If we draw an electrostatic potential plot of an alkene, we can see that alkenes are electron rich and the electron density of the pi bond is concentrated above and below the plane of the molecule, shown by this red region. In this electrostatic potential map, only the red region above the molecule is visible because the molecule or the diagram is tipped. The blue regions depict the comparatively electron deficient sites. The electron density of the pi bond is concentrated above and below the plane of the molecule, making the pi electrons more exposed than the sigma electrons. A strong electrophile has an affinity for these loosely held electrons and can pull them away to form a new bond, leaving one of the carbon atoms with only 3 bonds and a positive charge, which is called as carbocation. In effect, the double bond has reacted as a nucleophile, donating a pair of electrons to the electrophile. If we draw the electrostatic potential map of this carbocation, the electron deficient carbocation site is clearly visible by this blue color. Because the carbon-carbon pi bond of an alkene is much weaker than the carbon-carbon sigma bond, the characteristic reactions of the alkene is the addition reaction. One pi bond and one sigma bond are broken while the 2 sigma bonds are formed. Many different addition reactions are observed for alkenes, enabling them to serve as synthetic precursors for a wide variety of functional groups. The versatility of alkenes can be directly attributed to the reactivity of pi bonds, which can function either as weak base or as weak nucleophile. In many cases, addition reaction is simply the reverse of an elimination reaction. These two reactions represent an equilibrium that is temperature dependent. Addition is favored at low temperature, while elimination is favored at high temperature. To understand the reason for this temperature dependence, recall that the sign of del G determines whether the equilibrium favors reactants or products. Del G must be negative for products to be favored, while if the sign of del G is positive, reactants are favored. The sign of del G depends on the 2 terms, the enthalpy term and the entropy term. Let us consider these 2 terms individually, beginning with the enthalpy term. Many factors contribute to the sign and magnitude of del H, but the bond strength is the major factor. Consider this addition reaction. The value for bonds broken and bonds formed are given. If we calculate the del H for this reaction, we will find out that del H has a negative value. In other words, this reaction is exothermic, which is generally the case for addition reactions. Now let us consider the entropy term, minus T del S. This term will always be positive for an addition reaction because in an addition reaction, 2 molecules are joining together to produce 1 molecule of the product. This situation represents a decrease in entropy and del S will be having a negative value, whereas the temperature component, which is measured in Kelvin, is always positive for addition reactions. Combining these 2 terms, we can see that T del S will be positive for an addition reaction. Now let us combine the enthalpy term and entropy term. The enthalpy term is negative whereas the entropy term is positive. Therefore, the sign of del G will be determined by the competition between enthalpy term and the entropy term. In order for del G to be negative, the enthalpy term must be larger than the entropy term. This competition between the enthalpy term and the entropy term is temperature dependent. At low temperature, enthalpy term is dominant over entropy term. As a result, del G is having negative value, which means that products will be favored over the reactants at low temperature. In other words, the addition reactions are thermodynamically favorable at low temperature. However, at high temperature, enthalpy term becomes small while entropy term dominates. Therefore, del G becomes positive, which means that at high temperature, reactants will be favored. In other words, the reverse process elimination will be thermodynamically possible at high temperature. Now, this doesn't mean that all addition reactions are reversible at high temperature, because at high temperature, many reactants and products will undergo thermal degradation. Therefore, not all addition reactions are reversible at high temperature. The table here summarizes the classes of additions mostly shown by alkenes. The elements shown on the arrows are not the actual reagents used for these addition reactions, but depict simply the groups that appear in the final product. That means, for example, hydration is carried out in the presence of an acid called acid catalyzed hydration, or it may also be achieved by oxymercuration, demercuration, or it may also be achieved by hydroboration, oxidation. The dihydroxylation is carried out by KMnO4 in cold condition followed by oxidation. It may also be achieved by osmium tetroxide followed by oxidation. What's meant here is that the elements shown on these arrows are not the actual reagents, but just the elements that appear in the final product, while the reagents are different. We'll learn all these reactions one by one in the coming lectures. The stereochemistry of addition reaction is often important in delineating the reaction mechanism. Because the carbon atoms of a double bond are trigonal planar, there are two ways for the addition of elements like X and Y. The elements of X and Y can be added from the same side of the carbon-carbon double bond, in which case the addition is called as Syn addition, or the elements X and Y can be added from the opposite side of the carbon-carbon double bond, in which case the addition is called anti-addition.